for us, we want to calculate the pump GPM, which is, we said before, GPM equal Q, the heat loss for that entire loop, over 500 times 20, which is delta T, or it could be 30, but 20 is the most optimum one. And then we need to calculate the pump head in feet. What is pump head? Pump head is pressure. How much pressure that pump can provide. Why is it in feet? It's just a unit. We can convert that to Pascal or any other PSI, but feet is more common for pump selection, especially in HVAC. Okay, so GPM, again, this is the equation, and we get that. And remember, it's always per loop, so the entire loop, wherever the pump, if this is my pump here, whatever the entire loop is going to be, coming back all the way here, that is my pump requirements for the entire loop. What is the GPM? We can have a radiator here, another radiator here. So the entire loop BTUs is going to be obtained from the loop. That's the for the pump head. Okay, let's explain what is pump head and why is it required to be calculated in such manner. So, and what is the feet of water? So if I have a tube, and this tube is filled with, let's say, 1 foot, and it's filled with water. This water will exert pressure on 1 square inch. 1 square inch. If we have this tube, and the area of this circle here or base is 1 square inch, and I have the water weight acting on it. So this water weight per 1 square inch is called 1 foot of water. So this is why we have feet of water. Meter is very common internationally, but we can go to feet of water. So the required height, let's look at that. That's called static. That's the amount of height of water existing in the pipe to be lifting that water. So if this is my basement, first floor, second floor, third floor, and my boiler is here, and I have to pump water all the way to the top, that is my static head. How much water? If I say this is 8 feet, 8 feet, and this is 2 feet here because we're not going to the top, and this is 6 feet, so 2 and that's 8 by 3, that's 24 feet of height, and that's my static. I hope this makes sense. Okay, the other aspect, which is losses inside the pipe. Whenever we have a pipe and water running through it, water will behave in such manner that it will be fastest in the middle and it will stick to the sides in here, and that is problematic because it will hold back the water. So what happens is the losses due to friction will slow down the water, and we want to counteract that. So you need to supply more pressure to have that water going. And so that's the friction. The third part is fittings. So whenever we have a fitting, be it a 90-degree or a check valve, you will have resistance. And whenever you have resistance, you will have losses of pressure. Water will hit the wall here, then go up there, and eventually it will lose some pressure. So we need to account for that, and we can convert that into length. What would that loss of pressure will equal in length? What would that loss will equal in length? And to be consistent, again, we can't add apples to oranges. We want to have all of them in feet or meter. So is the fluid turning around? This is the pipe friction losses, and this is my pressure for height, which is static head as well. So pump curve, this is just for information. It's something you will obtain when you buy the pump. It comes with a curve. What does that mean? What is the curve? It gives you a function of the total head and the GPM. So the head is the pressure, and this is the flow rate. flow rate. So we'll say, how would that compare depending on the RPM? Can we just pump faster? Can we make the pump go faster? And what would that do? So there is something called performance curve. I keep doing the highlight. This is the performance curve, which is it's an experimentation that's done on the pump when they manufacture it to tell you what is the efficiency of that pump at certain RPM. So it does vary. You cannot just increase the motor speed to have the pump perform differently, because that will affect the efficiency. And we said before, what is efficiency? Hopefully somebody will shout it out right now. Is efficiency is output over input. So what is my input here? Electricity. And what is my output? Flow rate and pressure. So I can compare my RPM and efficiency giving this pump curve, and they give you the optimum, which meaning this pump will perform better. You have the better efficiency if you keep this pump running at this RPM. Here's an example. So this is the efficiency, and you see the total pump head here, and you will see also the gallon per minute over here, and these are the pump curves. If you stay within this pump curve, you should be fine. So this is giving you at the RPM, and this is the efficiency. If you go outside in that, you will have lack of efficiency. So that's something you want to look at if you're going to purchase pumps. And usually you can change the efficiency by going to different RPM, but this is what will happen. You have more, the efficiency will change based on the RPM, and there should be a percentage here at that point. The pump curve here, so head of water, and this is the pump curve. You want to maintain your pump operation around that pump curve in terms of head and flow rate. So we do understand now something about what is the pump curve, if you heard about it. So you know the pump curve and how would that pump compares, and probably that will affect the price of that pump and how does it perform. Okay, so going back to my equation components, we talked about static head, losses inside the pipe, and frictional losses. So this will be my height. Hopefully that's not going to be very difficult to calculate. It's the point from the boiler all the way to the top floor the system, and this is your height against gravity. Losses inside the pipes, amount of pressure required to friction, and pipe length. And fittings, we're going to count all the fittings that we have because they will be added into the equation. There are many ways to calculate pump head. There are many equations, many tables. I found that the most direct way and straightforward is something called the equivalent length method. And hopefully you'll find it easy. If you find any other way to calculate head, I will not be opposed to that. You can try to use that as well, but I found this to be the most easy one. The equation might look a little bit confusing, but it's not. So what we do, we will convert. So for the height, we have the height already in feet, so that's done with. For the length of the pipe, we have that also done with. So friction is going to convert into length. So we have the length of the pipe, we have the height of the pipe in feet. The third component is the elbows. We can convert elbows to length, straight length. So for example, we'll say this L shape can convert into 3 feet. 3 feet of length. And we can add all that together. So this component here, which is the LE, is the total length of the pipe, which include the pipe length and the elbows converted into straight length. That will be your LE, and you will divide that by 100. So this is the pump friction and fitting heads only. So that's how you convert your pump friction and elbows into head. So this is the complete length of the pipe and the complete total of elbows converted into length. A and B are coefficient that we'll get from the table, and GPM we already calculated, which is, we said Q over 500 times 20. Okay, so LE is the total length of the pump plus the length of the converted fittings, and A and B, this is not the pump, converted length of the pipes, sorry, this is pipes, plus the length of the converted fittings, and A and B are obtained obtained based on the GPM from the next table. So let's take a look. So this is for copper. Be aware it's only copper. And if we have, for example, 3/4 of an inch, one elbow, 190-degree elbow will convert to 2 feet of length, and so on. All these fittings will convert into length per foot. So as you can see, the 90-degree elbow will convert to longer than 45-degree because it's a sharper turn, and T's has a lot of losses. Divertities are very high because they do require a lot of pressure. Glow valve require a lot of pressure, and so on. So it's a complete direct lookup for the number of elbows you have. So one elbow will be 2 feet. So if I have 3 90 degrees elbows, will equal 3 times 2 will equal 6 feet in length. Equivalent length. That's what they call equivalent length. Again, we're looking here. This is how where we find those little A and B constants. Let's look at that a little bit. So this is based on the water temperature and the GPM range. And again, we are in this range here for the project and for our needs. So it's 3/4. So this is what we are going to look at. So let's highlight this area. This is my required sweet spot. So 1.75, if you notice that it does not change, B does not change, it's always going to be the same number. The water is mostly going to be 180 degrees. So this is going to be my A and this is my B, and the GPM range is within the acceptable limit. So I'll take those two, and this is going to be my A and B. All the other numbers you can always use if you have different design. But for now, this is going to be my A and this is going to be my B, and we're done. So A most likely is going to be always 0.274 and B is going to be 1.75. Alright, let's move on. Version for the, this is again for your range. Alright, so A and B for steel, A and B for copper, and we're good. This is an example. Let's look at this example and see what will happen. Series circuit, 150 feet. Okay, let me erase this. $150 feet of 1¼ copper tubing, 25 times 1¼ degree elbows, 2 ball valves, 1¼ pipe. What is the head loss for the circuit with 120 Fahrenheit and 15 GPM? That's just a lookup. So I want to find the equivalent length. I have 150 feet already. This is the length of the pipe. I don't have static. There is no static here. We just no static. So I'm doing only length. So 150 in here, and these are the elbows. Where did I get this number? From the table. This is the copper table, and I got this here, elbows and ball valves. These are the ball valves, 2 of them, and the 7 I got table from previous slide. And I looked up the A and B's. This is my A and this is my B for copper tubing. I divided the total length, which is, if we did this math, is going to be 239 feet. I put that in here, divide by 100, multiply by A, which is 0.0338, and then multiply by 15, which is the GPM. I have the GPM here, to the power of 1.75. You will ask me, how do I do that? If you look at your calculator, most calculators have this symbol here for power. So please try to look at your calculator and see how you can raise something to this funky power, because it's not 2, it's not 4. So you're gonna look in your calculator. Usually it looks like something like that, or it looks like something like that. So spend some time to look at your calculator and see what it looks like. Okay, that's an example. Another example, if we were to find the pump head required for a loop that goes to a house, second floor, at the height of 9 feet. The circuit contains 150 feet of 1/4 copper tubing and 25 9 degrees elbows. Makes sense, you can have a lot of 9 degrees elbows. 2 ball valves. What is the loss of the circuit? It seems like everything is the same, right? However, now this time we have a second floor, which means we have static. So there is static. So what is my static? That's the height. So the first thing, I will convert the tube length and the elbows into length. We did that. We know how we got those two things, just like previously. And from table 10, we went and got the A and B. We plugged it into the equation, and we got 9.2 feet. That is this part, friction and fitting length. What about the static? The static is going to be here, which is the second floor. That is 9 feet each. So 9 times 2, that's 18. Actually, it's 9 because it's only second floor. I'm going to this is my first floor. So probably I'm going to go from the boiler to the second floor, which is here. So this is going to be 9 feet, and I'm pumping only from the top to bottom. So this is my distance. So 9 feet static. This is static, and this is my converted feet, and that's going to be my pump head. I know it sounds a little bit like involved, but once you do a couple examples, it should be fine. So we have to look at the static head, tube length, and conversion from elbows to equivalent length. If you follow those tips, things will be a little bit less. Sheet on Blackboard, and the sheet will help you carry through the equation so you don't miss a step, and it's pretty straightforward. Just fill in the blanks, and I will put that on Blackboard so you can look at it. Alright, I'll stop now and I'll do the expansion tank in the next video. Thank you. I don't know if I have it here.